Good afternoon, everyone. This is going to be the third video of my practice exam review series, and if you do not know these videos, I basically just make them the Friday before an exam just to cover some tips and strategies that I used when I was taking this class to really prepare for these exams and succeed in them. Um, by this point in the semester, you should really know where you need to go and where the format is and how to properly fill this out. So it's just going to be first name, last name, signature, student ID number, check off your section, and you'll be provided an exam information sheet and an answer sheet. So before I even go into just all these questions broken down, I want to talk about two things that helped me when I took exam 3. First thing is drawing on the electronegativity periodic trend, and that goes from francium to fluorine from least to most. So this is least electronegative to most by fluorine. Another thing that I highly recommend just memorizing and writing down first thing the exam starts before answering any questions is this quick little chart. ED is electron domains, and hybrid means the hybridization is going to be. So if you have 2 electron domains, that's going to be an sp. If you have 6, that's going to be sp3d2. And that's just going to be very relevant whenever you're going to possibly have a question that asks you what is the hybridization orbitals. Cool. Other than that, you can always make up your own kind of mnemonic or figure to just draw in the beginning of the exam. I know for me, drawing out anything just helps me really retain that information, and it also helps out that I can retain that information, throw it on the exam information sheet or just anywhere in a blank piece of paper, and it results in me remembering things during the exam if I forget. Alrighty, so usually I always say to really go over the free response questions first, and I still think this is true for exam 3. A little less stress on this one though, because for a lot of people, most people just take a lot of time with the math and not really drawing out Lewis structures or doing VSEPR theory or doing hybridization. That stuff, if you have been practicing as much as you should not take too long for this exam. So if you want to start with the multiple choice, go for it, but safest bet is to always start with the free response questions. All right, let's get into this. Question 18 is PHO and shows minimized formal charges in a box provided, shown them pairs as dots, bonds as lines, and all non-zero formal charges on the appropriate atom in the structure. Cool. So how do we determine the center atom of a Lewis structure? It is usually going to be the least electronegative atom. However, we see that hydrogen here, if you look at the periodic trend that we just wrote, hydrogen is technically least electronegative. However, it only has an s orbital, so it can only have one bond. So our other option, which is going to be our option, is phosphorus. In the middle, oxygen on the outside, and we can have two options here. We can either throw this hydrogen here, or we can throw it on here. In this instance, I'm going to show just the right answer when it goes to here. And if you throw the hydrogen on the oxygen, that's okay. It will be very obvious when you check for formal charges that if you put the hydrogen on the oxygen, the formal charge for oxygen and phosphorus is not going to be minimized. Alrighty, and before that, let's just recap on how many electrons we need for this. Phosphorus has 5 valence electrons, plus 1 from hydrogen, plus 6 from oxygen. So we have 12 valence electrons we're looking with. We used 1, 2, 3, 4 to make those 2 bonds. So we're left with 8 electrons. Cool. So next rule in going in making these Lewis structures is just to throw all these electrons on to the outside atom. So in this case, it's just going to be oxygen since, hydrogen cannot have more than 2 electrons. It only has that s orbital. So now we're left with 2 electrons, and I'm going to throw this on phosphorus. Alrighty, big issue here. We don't have to check at formal charges. We don't have to do anything. Octet rule for phosphorus is not going to be fulfilled. While phosphorus does have the exception of being within the 3p period where it can have an expanded octet, that's only an expanded octet. This is not boron where it can have 6 valence electrons and be fine. It needs at the very minimum 8 valence electrons to fulfill that octet. Maybe more if we're talking about something that has an sp3d or sp3d2 hybridization. Best way to fix that is we can take, let's just take these 2 lone pairs and make a double bond here. So the octet rule for oxygen and phosphorus is fulfilled. Cool. So now we have a valid Lewis structure for octet rules. Let's just make sure that we have minimized formal charges. So formal charges should reflect the overall charge in a molecule. So if we have any formal charges, they should all net to 0, since this is a neutral atom or molecule. Hydrogen, we have 2 valence electrons minus 1 electron minus, no dots here, minus 2 over 2 because that represents that 1 bond right here. Now, this is how Dr. Outlaw taught you. I like to think about it that this 2 out of 2 really simplifies to 1. So if you want to think about it like 2 valence electrons minus dots, which is going to be here, subtracted by lines, which I only see 1 line, and mathematically 2 over 2 and 1 is the same thing. These converge and result in the same answer. This is a 0 formal charge. Cool. Now let's do that same math with the dots minus lines just to further show that this works. So Dr. Outlaw way and the way that we were taught in class, 5 valence electrons. I see 2 dots plus I see 1, 2, 3 bonds. Since each bond contains 2 electrons, that's 6 divided by 2, and that's going to result in 0 formal charge. And if you do the way I like to do it, dots minus line, or dots plus lines, I see 2 dots and I see 3 lines, that's also 0. Okay, and then oxygen, that's 6 minus, I see 4 dots and 2 lines, that's 0. And if you do Dr. Outlaw's way, results in the same formal charge. Again, doesn't matter, just as long as you show that work and you show all the things that the question is asking for, aka non-zero formal charges, lone pairs as dots, bonds as lines. Alrighty, cool. Going on to question 19, we have the Lewis structure of carbon dioxide, and we are given 4 possible hybrid energy diagrams shown below. Using only one of the diagrams, complete the correct energy diagram for the carbon atom. So really only focusing on this guy right here, by showing the position of the valence electrons. Place a circle around the electrons that are involved in pi bonding. And that's it. Alrighty, so looking at carbon dioxide, how many electron domains are there? If you're thinking 2, that is the correct answer. And I know some people see two lines and you're thinking two electron domains. I want to throw that out of the water. If you see any bonding, doesn't matter if it's a single, a double, or a triple, those all are one electron domain. Same thing with lone pairs. Each dot doesn't represent a lone pair, it only represents one electron domain. And we haven't really discussed with this in class or have really, I don't think we're required for the exam, but radicals also count as an electron domain. Cool. So if you remember that little chart that we drew, or you probably should memorize and write on your exam, hint, hint, nudge, nudge, two electron domains is equivalent to sp hybridization. So if carbon, just normal carbon at the third energy level, has a 3s that has one orbital and a 3p that has three orbitals, sp means that we take one of these guys and one of these guys and throw them into a hybridized orbital called sp. So sp is going to look like this, and 3p, those remaining unhybridized orbitals, are going to look like this. So we should pick diagram 3. Cool. Now, when we are going to fill out this orbital diagram, you have to make sure that how you're filling it out makes sense. What do I mean by this? So carbon has 4 valence electrons, so we're only working with 4 electrons within this hybridized diagram. So I'm just tentatively going to throw all electrons up arrow in each orbital. And this is the correct answer if you look at it, and I'm going to tell you why. So remember, to complete a bond, you need to have one electron or 2 electrons shared in between an atom. If we have just that one carbon atom have an unfilled orbital just with one electron, and you can think about an electron coming from oxygen to fulfill that orbital and create a bond. Same thing happens here, same thing happens here, same thing happens here. And that makes sense because look at this. We have 2 double bonds. And if you remember from class, a double bond consists of 1 sigma bond and 1 pi bond. So let's just say this one's sigma, this one is pi. Same thing here. So a sigma bond comes from hybrid orbitals overlapping with each other, while pi bonds come from the p orbitals. So we have 2 pi bonds, 2 sigma bonds. I see 2 places where bonding happens in unhybridized orbitals and 2 places where bonding happens in hybridized orbitals, which makes sense. 2 sigma, 2 pi. And per the rules of, or the requirements for this question, you have to please circle around the electrons that is/are involved in pi bonding. These guys up here, which are the p orbitals, if we label this correctly, will be involved in pi bonding. P for pi. Cool. Continuing on. Number 20. Draw 2 Lewis structures for, what is this? Polyatomic ion, that is chlorate. In the left box for part A, obey octet rule for all atoms appropriate. Then, in the right box B, show the structure with minimized formal charges. For both structures, so all lone pairs, normal Lewis structures rules. And then also throw resonance structures if there is any. Or, sorry, misrepresented that. Only throw one resonance structure if there's multiple possible. Alrighty, so remember, part A, we have to obey the octet rule. But part B, we can minimize formal charges, meaning we can extend that octet rule. So normally, Cl, at the very least, it has to be bonded once. Q. So, chlorate. We have chlorine, which usually has 7 plus 6 times whoa, 3 times 6, doesn't matter the order there, but 3 oxygen, 6 valence electrons, plus 1. Remember, if we have an anion, that means we have an extra electron to work with. On the flip side, if we have a cation, that means we have one less valence electron we have to work with. So in total, this comes to math. 12, 18. We should be working with 26 electrons here. Okay. And then just to, at very minimum, bond everything together, we have used 6 electrons. All right, next rule of making any Lewis structure, just throw those extra electrons on the external atoms, so these oxygens in this case. So that in total will take 18 electrons. Alrighty, my Apple Pencil is not wanting to work right now. Bear with me. But overall, your structure, there we go. And it doesn't matter the orientation of these lone pairs, just as long as there's fulfilling the octet rule. That's all that matters. So right there, we just used 18 electrons, so we're left with 2 electrons. Let's just throw these 2 on chlorine. Alrighty. Now, let's check if everything checks out per our octet rule, which all these external oxygens have 8 electrons. So does that chlorine, so we're good. Now, we cannot stop here. First, this is a polyatomic anion, so we have to designate the charge with a negative. Then, per what the question's asking, all non-zero formal charges will have to be shown. So for this oxygen, I see 6 dots. 6 dots plus 1 line. That's a -1 formal charge. And since all these oxygens have the same bonding in lone pairs, all these are going to be negative. Now, for this chlorine, we have 7 valence electrons in chlorine. I see 2 dots plus 3 lines. So that's going to be a +2 formal charge. Circle that guy. And this makes sense because we have -3 if we add up all those -1 formal charges from the oxygen. And then since we have a +2 from the chlorine in the middle, that negates 2 negative charges for a net charge of -1, which is consistent. Alrighty, this is not minimized at all. So let's look at answer or part B and see how this will change if we realize that chlorine is within the 3rd principal energy level, so it can have an expanded octet. Sorry, I was just drawing the answer. All right, let's just discuss this real quick. Matter of fact, I don't even have to draw all this. Alrighty, so immediately when I have a fully drawn out molecule and it has no double bonding and we're trying to minimize formal charges, I start throwing double bonds just to see how that affects the overall formal charge. So for this oxygen, let's just make this a double bond. And let's see, we have 6 valence electrons. I see 4 dots in 2 lines. That formal charge is going to be 0 now. Look at that. Now, for this chlorine in the middle, this formal charge is going to be +1 because 5, sorry, 7 minus, and this should be, that was 7 over there. 2 dots plus 4 lines. That's going to be a plus 1. Cool. Now, is this fully minimized? I wouldn't say so. I can see where this atom right here, this oxygen, we can take a lone pair off, throw that into a double bond since chlorine is amazing and it can have an expanded octet since it's in the 3rd principal energy level or higher. This removes that formal charge. If you recalculate it, it's the same bonding as this guy we just talked about. And then when looking at the chlorine, we have still 2 dots and 1, 2, 3, 4, 5 lines. So that formal charge is going to be 0. And since at the very minimum, we're going to have at very least 1 negative formal charge because the overall charge of this molecule is -1, this makes sense. This is as minimized as possible. Alrighty. I know I'm going through these pretty quick. If you have any questions, please come to my office hours. Please come, just email me because I know this exam is actually on Monday. If you have any questions outside of that on exam 3 material or any material, please look at the syllabus and find those office hours for Hira, me, and Dr. Outlaw. Alrighty, last free response question. We have Lewis structure of iodine pentachloride, and we just have a table for this molecule. So I do want to talk about how to study for the VSEPR theory. I recommend basically having, let's say this is the front of the flashcard and then this is the back of the flashcard. So the front of the flashcard, I would have the generic structure of it. So let's just do a tetrahedral, generic tetrahedral. And I would ask electron domains, name, or electron domains, electron geometry, molecular geometry, and yeah, that would be it. So this one, it would have 4 electron domains. Then it would have a electron geometry of tetrahedral and molecular geometry of the same thing, tetrahedral. And I would make a card for every single instance of maybe even having this as a lone pair and seeing, oh, that is trigonal pyramidal for the molecular geometry, but still for electron domains and electron geometry of tetrahedral, and just route memorization. Why is this important? Because this question is basically that flashcard information thrown into a question. So I see 1, 2, 3, 4, 5, 6 electron domains. So this is 6 electron domains, aka octahedral. Then I see 1 lone pair, and if you did those flashcards right, 1 lone pair with a octahedral electron geometry will make it square pyramidal. Molecular geometry. Now, for any octahedral molecule, the idealized bond angles, that would be 90 degrees. That's also something I would throw on that flashcard. 90 degrees. And then hybrid orbitals, if you drew that little table I was referring to in the beginning of this video, another hint, hint, nudge, nudge, that is sp3d2. Now, let's draw it. So, I like drawing it normal octahedral. Just looks like this. We have two guys going away, two guys coming close. And I will just fill it out with our normal molecules. Now, ignore the lone pair for now. I'm just going to draw the chlorines real quick. Okay, Apple Pencil's not wanting to cooperate with me. But basically all I'm going to do is I'm going to write those 5 chlorines and then just remove one of those lines or dashes or wedges and just replace it with a lone pair. That's, in my opinion, the easiest way to draw these 3D molecules in a consistent manner, by basically just drawing everything out and then removing to keep consistent with the actual molecule. So I remove that pair, and that's a lone pair. Alrighty. And also, I want to note that if you do this, this also is correct. I just prefer putting 2 dots because it's easier. Alrighty, polarity. For this molecule, since not all of the possible 90-degree angles are fulfilled out, it has to be polar. But if you want to look at it in the dipole addition, vector addition manner, you can see all these guys right here, the dashes and the wedges, they're on a square plane. So if we have all 4 of these on a square plane on each 90-degree corner, they all cancel out. So this dipole cancels out this dipole. Same thing happens here. This dipole cancels out this dipole. Now, the only dipole we have left that's not canceled out is this dipole of this chlorine pointing directly down. So the net dipole moment would be directly down, aka polar. And also, you don't have to draw the dipole errors if you don't want to. That's not part of question E. And for question F, that's not, you just have to circle an answer. You don't have to show the dipole errors if there's any confusion there. Alrighty, we're done with all the free response questions, so let's just dive into the multiple choice. I also did want to mention, I've had some conversations with some people in my office hours about better test strategies outside of the do the free response questions first and then go on to the multiple choice, because they have found out that, free response questions take a bit longer and sometimes they don't really know how to pace themselves in that consideration. So what I recommend, maybe as an alternative if you are also running into that issue, is to just do 3, maybe 4 multiple choice answers, or just look at them and then do 1 free response question, and basically just try to evenly distribute your time between these 3 or 4 multiple choice questions and the free response question, so you can kind of pace yourself a little bit better. All right, cool. Now, number 1, which of the following atoms is most electronegative? Look at that. We drew that trend. Hint, hint, nudge, nudge. Please draw this trend. It will help you out a lot. Anything near the top right is going to be more electronegative, and I see oxygen right there. I don't see any chlorine or fluorine, so it has to be D. Alrighty. Now, number 2, which of the following bonds is most polar? And when we're talking about most polar, we're basically saying which has the highest difference in electronegativity. So I see fluorine bonded to fluorine, that's nonpolar. Immediately wrong. And then I see fluorine bonded to bromine, chlorine, and iodine. So if you look at that, we have chlorine, bromine, and iodine. I see that fluorine is up here, that's the most electronegative, while iodine is least electronegative, and then it kind of goes increasing from fluorine or decreasing from fluorine to chlorine, that's least, then bromine's least electronegative than chlorine, and then iodine is less than bromine. So B and C have to be wrong because the difference between F and I and then those other options are more. And then between BR and I, these guys are so close to each other compared to F and I. So it has to be answer choice A. Basically, just look at your electronegativity trend and see where is the biggest gap. Alrighty. What kind of bonds are present in the compound NaC2H3O2, aka sodium acetate? Well, if you recognize that this is acetate and this is sodium, obviously this has to be ionic. And 90% of us I've seen have made this mistake and only saw that ionic. That's cool. That's only between sodium and acetate polyatomic ion. But if we actually look at the polyatomic ion of acetate, looks something like this. Looks something like this. Do we see these kind of bonds here? These are carbons, by the way. Yeah, these are polar covalent bonds. So all to say is, although this may have an ionic bond, if we look at the polyatomic ion, that polyatomic ion is composed of polar covalent bonds. So the actual answer will be answer choice oh, that's weird. Oh, sorry about that. So I did say there's polar covalent between the carbon and oxygen, but look at this carbon-carbon bond. That is nonpolar covalent. So on the actual answer key, it should have ionic, polar covalent, and then nonpolar covalent, aka pure covalent bonds. I think that was a typo. Yeah, that's a typo. So if that answer choice E had that nonpolar covalent, that would be right. Alrighty. Answer choice or question 4, which molecule ion does not have the number of valence electrons shown correctly? Okay. Nitrogen. That normally has 5 valence electrons. Since there's 2, 5 times 2, that's 10. Then ammonia. Nitrogen usually has 5. Then we have 4 hydrogens with 1 valence electron. So a lot of you would say, oh, there's 9 valence electrons. Look at this plus sign right here. That means we're dealing with 1 less valence electron, aka minus 1. That would be 8. 3 times 6 for 6 valence electrons. Sorry. Then H9, that would be, or 8 times 1, that would be 20. Then H2, each hydrogen only has 1 valence electron, and if there's 2, there should only be 2 valence electrons. I see 4. Answer choice D is immediately wrong. Then with sulfate, we have 6, and then we have a total of 30, considering the 24 valence electrons from oxygen. Then if we have a negative 2 overall anion, we have 2 extra electrons, so 30 plus 2, that's 32. So answer choice is D. Alrighty, which of the following statements is true about the formal charges and Lewis structures? Alright, statement A, Lewis structures with formal charges further from 0 are favored. That's the opposite. We want minimized formal charges. B, in Lewis structure of the polyatomic ion, the sum of all formal charges should equal 0. That's not true. Remember, if we have a polyatomic ion, all the formal charges of those atoms comprising of that polyatomic ion should equate to the overall charge of that polyatomic ion. We discussed that in the free response questions. And then for C, for uncharged molecules, the Lewis structure where all formal charges equal 0 will be favored. That is true. We're trying to minimize charges. And then D, a positive formal charge should be placed on the more electronegative atom. That is flip-flopped. Something that's more negative should have a negative formal charge. So kind of think about like if we put a negative formal charge on carbon as opposed to fluorine, that wouldn't make sense. We would want to put that negative formal charge on fluorine because it's more electronegative. Cool. In which bond is the bond polarity shown correctly? Remember, dipole arrows go from the partial positive going to the partial negative. And it's shown like that. So whatever that plus is has to be more partially positive or least electronegative than what it's pointing to. And the answer choice, if you look at the periodic trend, carbon is least electronegative than oxygen. So we put that plus on the carbon and point it towards oxygen. So answer choice B. Cool. Number 7, draw the Lewis structures for the carbonate ion. Include all non-zero formal charges and any equivalent resonance structures. What sentence is true for the carbonate ion? Cool. I think, honestly, looking at the answer choices, we could get the true statement from carbonate ion, but let's just work our chops on Lewis structures. So carbonate is CO2 negative. Let me fact check myself. I'm pretty sure it's CO2 negative 2. I always forget these charges. Okay. CO3 negative 2. My fault. So CO3 negative 2 is carbonate. Obviously, least electronegative atom is going to be thrown in the middle. At the very least, we're going to have to throw 3 oxygens single bonded. Overall valence electrons we're dealing with is 4 plus 3 times 6 plus 2, which is going to equal to, mental math here, 18, 4, 6. We have 24 electrons we're working with. So we expended 6 electrons from just single bonding them all together. Let's throw all the external atoms a lone pair to fulfill their octet rules. And that costed all of our 18 electrons. Issue here is this carbon in the middle does not have a fulfilled octet. So we will have to take one of these lone pairs and double bond it. Now, if we're looking at the formal charges for everything, they should all equal negative 2. This oxygen right here should be 0 if you're doing the dots plus lines minus the valence electron calculation. So this would be 0, this would be negative, this would be negative, and then the carbon in the center will be a neutral. Yeah, neutral. Now, if you wanted to draw another resonance structure where, I'm not going to draw it, but you can draw one where this oxygen will have a double bond or this oxygen will have a double bond. That's equally valid. Now, we talked about this with resonance structures. These are basically instantaneous moments. So in reality, when we're looking at the carbonate ion, they're not specifically acting like a single bond or acting like a double bond consistently. They're kind of in that intermediate in between a single bond and a double bond. So how does that relate to our correct answer? Answer choice E is the correct answer, but I'll go through everything. The carbon bonds in the carbonate are all this CO bonds in the carbonate are all the same length. That is true because since these are all acting as an intermediate between a single and a double bond equally, all their lengths should be equal. Alrighty. Now, if you didn't get that or just could not remember that small detail that we talked about in class, process of elimination is going to be your best friend. Obviously, answer choice D, wrong because we drew this out. There's no triple bond. All atoms should not have a formal charge of 0 since the overall charge of carbonate is -2. There's going to be formal charges other than 0. And then B is wrong just because of how we minimize formal charges. And then A is wrong because remember, we just talked about this. All of the bonds, all of the CO bonds act as an intermediate between a single and a double bond. There's no one oxygen consistently acting like a double bond, aka stronger than the rest. It's all equal, all kind of in that 1 to 2 range of bonding. So that's why answer choice E is by process of elimination. Cool. Which of the following statements is false about the carbonate ion? We can use our drawing from question 7 to really answer this. Has overall charge of 0. It should have 24 valence electrons. Should have 3 valence structures, or 3 resonance structures because we can move that double bond in 3 unique positions. And then the hydrogen carbonate, bicarbonate, is a carbonate atom with an additional hydrogen atom. That is true if you remember your polyatomic ions from last exam, which, shocker, does not go away for Gen Chem 1. That has an additional hydrogen atom. Alrighty. Question 9, which electron domain is the carbon atom in the carbonate polyatomic ion? So if we look at this, remember, doesn't matter what kind of bond it is, as long as it's a bond, doesn't matter if it's single, double, or triple, it counts as a electron domain. And since we have 3 bonds, I don't see any lone pairs. 3 electron domains is consistent with trigonal planar electron geometry. Cool. Which of the following statements is false? Double bonds are shorter than single bonds. I think that's true. Triple bonds are stronger than double bonds. We covered that in class. That is true. The more electrons shared in a covalent bond, the shorter and stronger the bond. AKA, if we said that answer B or statement B is correct, aka triple bonds are stronger than double bonds, this should also be true. Then the Lewis structures show ionic bonding between atoms in ionic compound. We actually do not show any ionic bonding. We kind of throw them in their anion and cation forms because remember, Ionic bonding is not sharing electrons equally. They basically take, or the anion takes an electron from the anion or cation. And then a single bond involves sharing 2 electrons. Yep, that's true. Go. Which of the following molecules will have a Lewis structure that contains a radical? Alrighty. A lot of you will look at this question, and if you have been timing yourself when taking these practice exams, which I highly recommend, this may have been a question that took a while to figure out. I'm going to show you a very easy way to determine if a molecule has a radical. And that's simply if the overall valence electrons, if it's uneven, it has to have a radical somewhere. So if we look at answer choice A, 5 plus 5, that's 10, plus 6, that's 16. That's an even number. Wrong. NO2, 5 plus 12, that's 17. So this should be a radical. We will double check, but let's look at all the other answers. I see 4 plus 4, 8. Nope. I see, 3 plus 3, that's 6. Nope. I see 2 plus 2, that's 4. Nope. So looking at NO, this guy right here, we have 17 electrons to work with. We just use 4, so this should be math. 13. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So that's 12. So we have one electron left. Look at that. I don't have to completely look at the formal charges or just like minimize formal charges to see that there is going to be a radical in the nitrogen dioxide atom or molecule. And you can look at a picture on Google and you can see that this is a radical. Alrighty. And then just, again, reiterating, you don't even have to draw this out. You can just see by the amount of valence electrons that's uneven that it has to be NO2. Cool. Which of the following atoms will follow the octet duet rule? So, firstly, I would just look at all of the central atoms and just make sure that they're not in the 3p level. So I'm going to just copy this. And just go over those exceptions to the octet rule. So answer choice A, I see boron. Boron can have 6 valence electrons on it and be fine. So that's a little sus. I'm not going to completely mark that off as of yet until there's one that's undeniably unable to violate the octet rule. Sulfur, that is within the 3p level, so that can have expanded octet. So little sus, but not completely out of the game yet. And then fluorine dioxide, I'm looking at fluorine. This is also fluorine dioxide. This is looking at the third energy level or second energy level. So I'm pretty sure that this may be our answer, but let's also look at D, nitrogen trihydride. This might be a possible option. So let's just draw the Lewis structures of C and D and make sure that they all follow the octet/duet rule. So first, nitrogen trihydride. We have nitrogen in the middle, and we have 3 hydrogens. 1, 2, and 3. Now, let's just calculate how many valence electrons we're looking at. We have nitrogen, that's 5, plus the 3 from hydrogen. We have 8 valence electrons we're working with. And if we have spent already 6 here, we have 2 left. So the remaining option, and the only option, is to throw it on the central atom of nitrogen. So that follows all the octet rule. Let's look at C. I'm going to preemptively pick this as my option. Fluorine dioxide. Fluorine should... Fluorine, I'm going to put that in the middle. Interesting. Okay, so fluorine, that has 7 valence electrons, plus 6 from oxygen, plus a 6 from another oxygen. Remember, we just talked about radicals in the previous question. So this has 19 valence electrons. By definition, what we just stated in the last question, how we figured that out, that NO2 was a radical, was because it had an uneven amount of valence electrons. So although fluorine dioxide, the actual atoms would follow the octet rule, since there is not enough valence electrons to fulfill the octet rule, this structure would have a radical. So without a doubt, answer choice D is right. Alrighty. 13 of the 3-dimensional structures show below which may exhibit molecular polarity. I see, let's just go from right to left. I see NN right here. These are the same atom. They have no net dipole moment, so this is not true, not able to, not nonpolar. Then sulfur with these 3 oxygens surrounding it. If we drew dipole arrows, if you know how to do vector addition with your dipole arrows, you can see that these 2 oxygens right here, the up and down directionality kind of cancel out for a net like this. And then that net of these 2 dipole moments cancels out this dipole moment right here. So overall, this is a net 0 dipole moment, so no polarity right here. Then it's a very similar concept that we just covered with this trigonal planar atom or molecule with carbon tetrafluoride. Since all of these are distributed 109.5 degrees away from each other in equidistant orientations, all these net dipole arrows are going to cancel out. All of them cancel out in directionality up, down, left, right, coming towards you, going away from you. Then for this one, very similar concept. If we break down this trigonal bipyramidal structure here, just ignore these 2 right for now. This kind of triad over here is on a single plane, basically kind of looking like a trigonal planar molecule like this. So if we think about it the same way, these are equal strength dipole moments. They're all at the 120 degree orientation, so those all cancel out. Now, the only things that we're looking at is those 2 chlorines, the one going up and one going down. Those are 180 degrees from each other, so those will cancel out as well. So overall, there's going to be no polar molecules here. All right. Identify the number of sigma and pi bonds in a molecule below. Remember, each molecule, or sorry, not each molecule, each bond at the very least, for the purposes of Gen Chem 1 and basically all of your undergrad degree for going up to Orgo at the very least, has a minimum of 1 sigma bond. So a single bond, that is 1 sigma bond. Sigma, sigma, sigma. So we have 4. Now, looking at this double bond, that still holds true. At a minimum, each bond needs 1 sigma bond, and then anything on top of that has to be a pi. So a double bond both has a sigma bond and a pi bond. And then this does not show a triple bond, but a triple bond will have 1 sigma bond at the very least, and then have 2 pi bonds additionally on top of that. So the answer would be 5 sigma, 1 pi. Which of the following statements is false? Hybrid orbitals are shaped like lopsided dumbbells with 1 large lobe and 1 small lobe. That's true. We talked about that. What that is talking about is something like this shape. Kind of looks like an S, kind of looks like a P. Then, answer choice B, 4 sp3 orbitals can be produced by mixing 1 s, 2 p orbitals together. Nope. That is representing sp2. So this is our answer choice, but let's look at all the other options and make sure. Orbital hybridization is the most accurate model of covalent bonding. Nope. There are more accurate models that we have talked about in class. Or actually, no. Sorry. This is true. What was I saying? I don't know why I was thinking Lewis structures. Lewis structures is least accurate. And then the orbital hybridization, where we hybridize orbitals, that makes more sense, considering the bonding of everything. Then D and E are basically the definition of sigma and pi bonds. So sigma bonds are created by overlapping of hybrid orbitals, while pi bonds are unhybridized p orbitals. So B is the only statement that is false. Alrighty, 16. If we look at all of our answer choices, immediately I'm looking at E. That's wrong because S, sphere. Then P, I like to think of it like a peanut. So B is wrong. Now, SP kind of is in between. It has a sphere and then it has a peanut. I kind of like to think of it like a SP kind of looks like a pear. So answer choice A has that pear. While all these other ones, C, that's just another p orbital, and then D, that is definitely not an sp orbital right there. Alrighty. 17. In which partial Lewis structure does nitrogen have a non-zero formal charge? Remember, nitrogen has 5 valence electrons. So if we do the framework that I use, the dots plus lines, I see answer choice A has 4 dots plus 2 lines. So 5 minus 6, that's -1. So that should be our answer choice, but let's look at all the other ones. I see 2 dots, 3 lines, 5 minus 5, 0. 2 dots, 3 lines, same thing, 5 minus 5, 0. Then 3 lines, 2 dots, 5 minus 5, that's still 0. So answer choice A should be the right one. Alrighty. Well, that covers all of practice exam 3. I highly recommend, just with any practice exam, please time yourself when taking these exams. If you have literally any questions regarding how to succeed on this exam or just any questions on the material itself, please reach out to me via email or come to my office hours. Thank you.